Hello, in this lecture I will answer two questions. In the first question, you find out the area of this semicircle that is inside the big quarter circle AOB. In the second question, you find out the area of this ring shape. So we start with the first question. The drawing, we have quarter circle AOB. This is angle AOB, this is right angle. Right side OS equals to 4 units length. We also know that arc AQ is equal to arc QB in its length. Again, our test is to find out the area of this semicircle. So first of all, we define the center of this semicircle. This point is point C. We define the touching point of the big quarter circle with this semicircle. This point is point P. We define the radius of this semicircle as R, so CP is the radius of the semicircle. Is equals to R. Likewise, CQ is also the radius of the semicircle. In the next step, point S is the point of tendency obtained OB with this semicircle. So we join points C and S together by straight line. Point C is the center of the semicircle. Point S is the point of the semicircle itself, therefore CS is the radius of this semicircle. This equals to R according to our definition. Here we can implement rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So we have the radius CS is equals to R. Radius CS is drawn to point S. This is the point of tendency obtained OB with this semicircle. And now your radius is drawn to the point of tendency, then tangent to OB will be perpendicular to the radius SC. OB is perpendicular to SC. It means that this angle equals to 90 degrees. And this angle also equals to 90 degrees inside according to rule 1. In the next step, we will do a construction. That is to say, from this point Q, we will go perpendicular on OB. Again, from point Q, we will go perpendicular on OB. We will define the touching point of the perpendicular from point Q and OB. This point is point M. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. QM is the perpendicular on OB. So here we can implement rule 22. According to rule 22, if the sum of two one-sided triangles is equal to 180 degrees, then they are located between parallel lines. In the drawing, we have line A and line B. The red line C cuts those two lines and those 2 points. In addition, those triangles alpha and beta are defined as one-sided triangles. So if the sum of those two angles is equal to 180 degrees, that is to say if alpha plus beta equals to 180 degrees, then they are located between parallel lines. That is to say, line A is parallel to line B. So we can implement rule 22 in our drawing. When we put in our drawing, both circles are defined as one-sided interrogals. The sum of those circles is, of course, 90 degrees plus 90 degrees is equal to 180 degrees. According to rule 22, if the sum of two one-sided interrogals is equal to 180 degrees, then they must be located between parallel lines. That is to say, PO is parallel to CS. Is parallel to CS. According to rule 22. PO is parallel to CS. Likewise, according to rule 22, those two one-sided interrogals, the sum of those two one-sided interrogals is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, CS is parallel to QM. CS is parallel to QM. Likewise, the sum of those two one-sided interrogals is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, PO is parallel to QM. PO is parallel to QM. So if you found out that those three lines with PO, CS, and QM, they are parallel to each other. So we have three parallel lines. Line 7 QM connects those three parallel lines together, and line 7 MO also connects the three parallel lines together. And therefore, whenever you have three or more parallel lines that are connected with two other segment lines, line segments, you can implement Taylor's theorem. This is Taylor's theorem. According to Taylor's theorem, here PO is parallel to CS is parallel to QT. Line 7 PQ connects those three parallel lines together. Likewise, line 7 OT connects those three parallel lines together. Actually, a special relationship exists between those two segment lines that are not parallel to each other. Between those two segment lines, line segments, that connects those three parallel lines together. The following relationship exists between those two line segments, PQ and OT. PC over CQ equals to OS over ST. Again, PC over CQ equals to OS over ST. So, according to the theorem, we get that PC over CQ equals to OS over SM. So, write it down. But again, PC over CQ equals to OS over SM. according to test theorem. So, according to test theorem, the following relationship exists between those two isomers that connects those three elements together. PC over CQ equals to OS or SM. PC is R, CQ is also R. That is R over R equals to OS. OS is 3. Or SM. SM is the missing side, so we leave it as it is. So for that, if you found out that R over R equals to 3 over SM. R over R is 1, so 1 equals to 3 over SM. One equals to 3 over SM. Here we multiply this equation by SM. So we get that SM equals to 3 units in its length. This is line segment S7 is equals to 3 units in its length. In the next step, we join points O and Q together by straight line. By joining points O and Q, create a right triangle QOM. Point O is the center of the quarter circle, and this is angle AOQ. Angle AOQ subtend on arc AQ. Likewise, this is angle, so it is a center angle that subtend on arc AQ, because point O is the center of the quarter circle. Likewise, this is center angle QOB that subtend on chord QB. But it is given us a question that arc AQ is equal to arc QB in its length. Arc AQ equals to arc QB. So here we can implement rule 23 in our drawing. Okay, click on rule 23. According to rule 23, center angles that subtend on equal arcs are equal to each other in their sizes. In the drawing, we have a circle. This is center angle AOB that subtend on arc AB. Likewise, this is center angle COD that subtend on arc CD. If arc AB equals to arc CD in its length, then those two perpendicular that subtend on arc AB and arc CD correspondingly must become to each other in their sizes. That is to say, alpha equals to beta, or central angle AOB equals to central angle COD in its size, so alpha equals to beta. So whenever you have two central angles that subtend on equal arcs, they must be equal to each other in their sizes. In this case, if arc AB equals to arc CD, then alpha equals to beta. So we have those two central angles subtend on equal arcs, right? Because central angle AOQ subtend on arc AQ, central angle QOB subtend on arc QB, arc AQ equals to arc QB. So those two central angles subtend on equal arcs, and therefore they must be equal to each other in their sizes according to Rule 23. So if we define the size of this angle as theta, then the size of this angle must be also equal to theta, because they are equal to each other according to Rule 23. The big angle AOB is a right angle, and therefore theta plus theta equals to 90 degrees. 2 theta equals to 90 degrees. And therefore theta equals to 45 degrees in its size. This is angle theta that equals to 45 degrees in its size. So in the right triangle QOB times 45 degrees equals to QM over MO. Again, the right triangle QOM times 45 degrees equals to QM over MO. Repeat again. The right triangle QOM times 45 degrees equals to QM or MO. Times 45 degrees is 1. So 1 equals to QM. QM is the missing side, so leave this it is. Over MO. MO in total equals to 3 plus 3, that is 6. So in total, we have found out that 1 equals to QM over 6. Here we multiply this equation by 6. And finally we get that QM, the missing estimate QM, is equal to 6 units in its length. This is the missing side QM. This is equals to 6 units in its length. In the next step, we will do a construction. That is to say, from point C, that is the center of this semicircle, we will go perpendicular on QM. Then from point C, we go perpendicular on QM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and QM. This point is point L. By doing this construction, we can do quadrilateral CLMS. Inside this quadrilateral CLMS, we have 1, 2 right angles. The sum of right angles is 270 degrees. So 270 degrees plus the size of this 450 degrees. In total, it must be equal to 360 degrees according to the rule. It says that the sum of the angles in any quadrilateral is equal to 360 degrees. Is equal to 360 degrees. So therefore, this missing angle was equal to 90 degrees in its size. So in quadrilateral CLMS, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this right angle, if not a square. So we relate to quadrilateral CLMS as a right angle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CLMS, side CS is equal to the opposite side LM. But CS is out, therefore the opposite side LM must be equal to our units instead. Likewise, according to the same rule, in the same rectangle CLMS, side MS must be equal to the opposite side CL, but MS is 3, therefore the opposite side CL must be also equal to 3 units in its length. What is the length of this missing 97 QL? QL equals to QM minus LM. Again, QL equals to QM minus LM. So, as you know, QL equals to QM minus LM. So QL equals to QM, that is 6, minus LM, that is R. So in total, QL equals to 6 from 7 in its length. In the next step, I'll copy this right small triangle CQM in the new page, and we'll implement the Pythagoras theorem on this small right green triangle CQM. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the version for Pythagoras theorem. So actually this is the right triangle QCL, this is according to the original drawing. This right triangle QCL, according to the Pythagoras theorem, QC squared, that is the square of the hypotenuse, equals to QL squared plus CL squared. So I write it down. QC squared equals to QL squared plus CL squared. QC is R, therefore QC squared is R squared equals to QL squared. QL is 6 minus R, therefore QL squared is 6 minus R squared plus CL squared. CL is 3, therefore CL squared is 3 squared, that is 9. So in total, we have found out that R squared equals to 6 minus R squared plus 9. So R squared equals to 6 minus R squared. 6 minus R squared equals to 6 squared, that is 36, plus R squared, minus 2 times 6 times R, that is minus 12R, plus 9. So here we have R squared on both sides of this equation, so R squared again cancelled. After cancelled R squared, in this side of the equation we left with nothing, that is to say 0. While on the other side of the equation we have 36 plus 9, that is 45, minus 12R. So in total we should know that 0 equals to 45 minus 12R. Here we add 12R to this equation. If I can get that 12R equals to 45, here we divide this equation by 3. If I can get that 12R over 3 is 4R, equals to 45 over 3 is 15. So 4R equals to 15. Here we divide this equation by 4. If I get that the radius R of the semicircle is equal to 15 over 4 units in its length. Our task is to find out the area of this semicircle. So after you know that the area of any semicircle is equal to the area of the circle, that is pi r squared over 2. And therefore the area of our semicircle must be equal to pi over 2 times r squared. R is 15 over 4, therefore r squared is 15 over 4 squared. So the area of our semicircle must be equal to pi over 2 times 15 over 4 squared. So therefore equals to pi over 2 times 15 over 4 squared. 15 squared is 225 over 4 squared, that is 16. So to that, therefore semicircle equals to 225 pi over 16 times 2 is 32. So therefore the semicircle equals to 225 pi over 32 square units in its size, or in terms of numbers it is equals to 22.09 square units in its size. So again, now this this semicircle equals to either 225 pi or 32 square inches in size, or in terms of numbers, the area of this semicircle equals to 22.09 square inches in size. So we finished with the first question. In the next step, I will present you the second question and solve the second question of this lecture. Our task in the second question is to find out the area of this green shape. So, in the drawing, we have the right angle ABC. ABC is right angle, angle BC is right angle. We know that side AB of the angle ABC is equal to 6 units in itself, side AC equals to 8 units in itself. The length of the opposed BC is the missing side. Inside this right angle ABC, we have those two identical circles. Again, our task is to find out the area of this green shape. So first of all, we'll find out the hypotenuse BC of the right angle ABC. So according to the Pythagoras theorem, this right angle ABC BC squared, that is the square of the hypotenuse, equals to AB squared plus AC squared. So as you know, BC squared, that is the square of the hypotenuse, is equal to AB squared plus AC squared. So again, according to the Pythagoras theorem, the right angle ABC, BC squared equals to AB squared plus AC squared. BC is the missing side, so we'll leave it as it is. So it is BC squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36, plus AC squared. AC is 8, therefore AC squared is 8 squared, that is 64. And so that actually found out that BC squared equals to 36 plus 64, that is 100. BC squared equals to 100. Here we'll take out all of this equation, and we get that everything on the hypotenuse BC is equals to the square root of 100, that is 10. This is the missing hypotenuse BC is equals to 10 units in its length. In the next step, we find out the area of this right triangle, triangle ABC. The area of right triangle equals to the base of the triangle times the height over 2. So the of this triangle ABC must be equal to the base AB times the height AC over 2. And again, the of this triangle ABC is equal to the base AB times the height AC over 2. AB is 6, AC is 8 over 2. So 6 times 8 is 48 over 2 is 24. And to that we found out that the area divided by ABC is equal to 24 square units in size. The next step, we'll find out the of this triangle ABC in a different way. We choose the base of triangle ABC is BC, then the height to the base, that corresponds to the with the base BC, will be defined as H, and therefore the of triangle ABC must be equal to the base BC times the height H over 2. So the of triangle ABC is equal to the base BC times the height H over 2. And again, the height H must get by the rest with the base BC. So we found out that the triangle ABC equals to 24 and it equals to BC. BC is 10. Times H over 2. 10 over 2 is 5, so in total this expression equals to 5H. So 24 equals to 5H. Here we divide this equation by 4 and by 5. Get it H, the height to the base H equal to 24 over 5, that is 4.8 units in its length. So the height H to the base BC equals to 4.8 units in its length. In the next step, we define the center of this circle as P. This point is P. Likewise, we define the center of this identical circle. This point is point Q. We define the point of tendency of tangent BC with this circle. This point is point L. We define the point of tendency of tangent BC with this circle. This point is point K. We define the point of tendency of tangent AC with this circle. This point is point J. And finally, we define the point of tendency of tangent AB with this circle. This point is point G. To define the radius one circle is R, so because of the fact that those two circles are identical, they must have also the same area on the eye. So the radius of this circle is also equal to R. So in the next step, we join points P and M together with such line. Point P is the center of this circle, point L is the point of the circle itself, therefore PL is the radius of this circle, is equals to R. So the radius PL is equals to R, the radius PL is drawn to point L, this is the point of tendency of tangent BC with this circle. Whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius LP. If BC is perpendicular to LP, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we join points Q and K together with such line. QK is of course the radius of this circle is equals to R. Point K is the point of tendency of tangent BC with this circle. And therefore, according to rule 1, this angle equals to 90 degrees. This angle also equals to 90 degrees. In the next step, we'll define the touching point of those two circles. This point is point M. In the next step, from point M, this is the touching point of those two circles, we will go perpendicular on BC. Again, from point M, we will go perpendicular on BC. Okay. This angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point M and BC. This point is point T. What is the definition of line segment MT? Line segment MT is a common tangent that belongs to both circles. Line segment TM is the tangent to this circle at point M. Line segment TM is also tangent to this circle at the same point M. Therefore, line segment TM is a common tangent. Line segment TM is a common tangent that belongs to both circles. In the next step, we join points P and M together by a straight line. We define the radius of one circle as x. PM is of course the radius of this circle. Is equals to x according to our definition. The radius PM is equals to x. The radius PM is drawn to point M, that is the point of tendency of tangent TM in this circle. And now your radius is drawn to the point of tendency, then tangent TM will be perpendicular to the radius MP. If TM is perpendicular to MP, it means that this angle equals to 90 degrees according to rule 1. So actually, in quadrilateral PMTL, we have 1, 2, 3 arteries. The sum of 3 arteries is 270 degrees, so 270 degrees plus the size of this 4 facing angle. In total, it was equal to 360 degrees according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 p circle must be equal to 90 degrees in its size. So for the other one, this for the other one, PMTL is 4 rectangles. Therefore, according to rule 5, it is a rectangle. Now, in the next step, we join points Q and M together by a straight line. QM is of course the radius of this circle, equals to x. Again, point M is the point of tendency of tangent here with this circle. So according to 1, this angle equals to 90 degrees. I will not repeat on the same explanation. It's very clear that according to 1, this angle equals to 90 degrees in its size. This is the big angle PMQ. The big angle PMQ equals to 180 degrees in its size. And we know that any angle that is equals to 180 degrees in its size, it is defined as a straight line. Therefore, PMQ is a straight line. So if you know, PMQ is a straight line because angle PMQ equals to 180 degrees in its size. PMQ is a straight line. In the next step, I'll prove that line segment PMQ is one straight line according to rule 10. Those two circles touch each other externally at point M. That is to say, they have an external edge between them at point M. And whenever there are two circles with an external edge between them, you can implement rule 10. So I can click on rule 10. According to rule 10, if two circles touch each other externally, then the straight line which connects the circles together passes through their touching point. In the drawing, we have those two circles that touch each other externally at point P. Point O is the center of this circle, point M is the center of this circle. The straight line that connects the circles together is of course the straight line OM. And according to this rule 10, according to this rule 10, the straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass through point P, that is their touching point. Or in other words, OPM is one straight line. Again, OPM is one straight line according to this rule 10. Okay, I'll show you implement rule 10 in our drawing. Why? Because in our drawing, those two circles have an external edge between them at point M. So, point P is the center of this circle, point Q is the center of this circle. The straight line that connects the circles together is of course the straight line PQ. According to rule 10, the straight line PQ must pass through their touching point, that is point M. Again, the straight line PQ according to rule 10 must pass through point M, that is their touching point, or PMQ is one straight line. So, we prove that PMQ is a straight line in two different methods. The first method, because of the fact that angle PMQ equals to 180 degrees inside. Therefore, PMQ must be a straight line, because any straight line, any angle that equals to 180 degrees inside must be a straight line. Therefore, PMQ is one straight line, and according to rule 10, PMQ is also one straight line. Okay, so in this quadrilateral MTKQ, we have 1, 2, 3 rectangles, and therefore this fourth angle must be equal to 90 degrees in its side. And let's repeat on the same explanation. It's very clear that this angle must be equal to 90 degrees in its side. So that is actually quadrilateral MQKK has 4 rectangles, and therefore it is a rectangle. What about the big quadrilateral PQKL? In quadrilateral PQKL, we have 1, 2, 3, 4 rectangles. Therefore, the big quadrilateral PQLK is a rectangle. So the big quadrilateral PQLK is a rectangle because it has 4 rectangles. You actually found out that PMQ is one straight line. PMQ is one straight line, and therefore PMQ equals to, because of the fact that PMQ is one straight line, PQ in total must be equal to PM, that is x, plus MQ, that is x. So in total, PMQ equals to x plus x, that is 2x. So if you know, we know that 97 PMQ or can write down that PQ, if PMQ is a straight line, of course PQ is also a straight line. So PQ is a straight line, and it is equals to 2x units in its term. This is line 7 PQ, is equals to 2x units in its term. So in rectangle PQKL, the big rectangle PQKL, side PQ must be equal to the opposite side LK, but PQ is 2x, therefore the opposite side LK must be also equal to 2x units in its length. And k equals to 2x. In the next step, I'll copy this big rectangle PQKL in a new page, in a new drawing. And in the new drawing, we'll construct the height to the base BC of triangle ABC. Repeat again. In the new drawing, we'll construct the height H to the base BC. So first of all, I'm copying this rectangle PQKL in a new drawing. Actually, this is rectangle PQKL that I copied from the original drawing. We already found out that LK equals to 2x. Likewise, PQ also equals to 2x unit in itself. PL is the radius that is x. QK is also the radius that is x. Those four angles are all right angles because PQKL is a rectangle. So in the next step, I'll construct the height to the base BC of triangle ABC. Again, the height to the base, the height h to the base BC must create 90 degrees with the base BC. So actually, you have to draw a perpendicular from point A on BC, and this will be the height to the base BC. We define the height to the base BC as h. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point T. Likewise, we define the intersection point between side the height AT and PQ. This point is point J. So actually, by doing this construction, we get those two quadrilaterals, small quadrilaterals. This is the small quadrilateral JQKT. So this small quadrilateral JQKT, we want two further, so therefore this 4 pieces, this 4 pieces must be equal to 90 degrees in size. Likewise, this small quadrilateral PJTL, we want two further, and therefore this 4 pieces must be equal to 90 degrees in size. So in both quadrilaterals we have 4 rectangles, and therefore they are both rectangles. Now, we know that the opposite sides of a rectangle are parallel to each other. Repeat again, the opposite sides of a rectangle are parallel to each other. So, in this rectangle PJTL, PJ is parallel to LT. Those two opposite sides are parallel to each other. Those two angles are defined as corresponding angles, and are located between the parallels PJ and LT. And therefore, they are equal to each other in their sizes. But this angle was 90 degrees, and therefore this missing angle must be equal to 90 degrees in size. Likewise, in rectangle JQKL, side JQ is parallel to the opposite side TK. Those two corresponding angles are located between the, actually, those two corresponding angles are located between the parallels JQ and TK, and therefore they must be equal to each other and their sizes. But this angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees in size. According to the rule, that corresponding angles between parallel lines are equal to each other. So the next step, we find out, so in rectangle PJTL, side PL equals to the opposite side JT, but PL is x, therefore the opposite side JT must be also equal to x units in its length. What is the length of AJ? AJ equals to AT minus JT. And again, let us say that AJ is equal to AT minus JT. So AJ equals to AT. According to our definition, the I to the base BC that is 80 equals to H. Again, 80 equals to H. And we already found out that H equals to 4.8 units in its length. So 80 is equals to 4.8 minus JT. JT is X. So in total, we actually found out that, let me say 97 AJ equals to 4.8 or 6 units in its length. So in the next step, we join points A and P together by side 9. And we join points A and P together by side 9. Doing those constructions, we got to do triangle APQ. This is triangle APQ. If we take the base of triangle APQ is PQ, then the height of the base will be AJ. Why AJ is the height? Because it creates 90 degrees with the base PQ. And therefore it is very clear from the drawing that there are this small triangle APQ must be equal to the base PQ times the height of the base AJ over 2. Again, the APQ equals to the base PQ times the height of the base AJ over 2. Again, AJ is the height of the base because it creates 90 degrees with the base PQ. Those triangles are both right angles. So at another, we found out that the area of this small triangle APQ in total it is equal to the base PQ times the height AJ over 2. Repeat again, the area of this small triangle APQ in total is equal to the base PQ times the height of the base AJ over 2. We already found out that PQ, the base PQ, equals to 2x units in its length times the height AJ. AJ equals to 4.8 minus x. Over 2. So in total, we found out that the area of this triangle APQ is equal to 2x times 4.8 minus x over 2. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled. So we left only with x times 4.8 minus x. and open the brackets of this expression and get that x times 4.8 is 4.8x. X times minus x is minus x squared. So in total, we found out that the area of the small triangle APQ is equal to 4.8x minus x squared in its size. The area of this triangle APQ in total it is equal to 4.8x minus x squared in its size. In the next step, we define the point of tendency of tangent AB with this circle. This point is point S. And we join points P and S together by a straight line. PS is of course the radius of this circle. It is equal to x. Point S is the point of tendency of tangent AB with this circle. Therefore, according to rule 1, this angle equals to 90 degrees, and this angle equals to 90 degrees. Likewise, we define the point of tendency of tangent AC with this circle. This point is point Y. We join points Q and Y together by a straight line. QY is of course the radius of this circle, equals to x. Again, according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees in its size. In the next step, we join points P and B together by a straight line. Likewise, we join points Q and C together by a straight line. Actually, by doing all those constructions, we divided the big right triangle ABC into 6 parts. That is to say, the first part of triangle ABC is this triangle APB. The second part of triangle ABC is triangle AQC. The third part of triangle ABC is this right triangle PLB. The fourth part of triangle ABC is the right triangle QKC. The fifth part of triangle ABC is rectangle PQKL. And finally, the sixth part of triangle ABC is triangle APQ. It is very clear that the area of triangle ABC must be equal to the sum of the areas of the three shapes that it consists of. So, right now, the area of triangle ABC in total must be equal to the area of the first shape that the triangle ABC consists of, especially the area of this triangle APB. That's the area of the second shape that triangle ABC consists of, the area of this triangle AQC. That is the second shape that triangle ABC consists of. Plus the area of the third shape that triangle ABC consists of. The right triangle PLB. Plus the area of the fourth shape that triangle ABC consists of. And the right triangle QKC. Plus the area of the fifth shape that triangle ABC consists of. Is the right triangle PQKL. Plus the area of the six shapes that triangle ABC consists of. This is triangle APQ. And again, now triangle ABC must be equal to the sum of the areas of the six shapes that it consists of. The first shape is triangle APB, plus the area of the second shape that is triangle EQC, plus the area of the first or the third shape of triangle ABC that is triangle PLB, plus the area of the fourth shape that is actually the area of the right triangle QKC, plus the area of the fifth shape that triangle ABC consists of. That is actually the area of right triangle PQKL, plus the area of the sixth shape that triangle ABC consists of. That is actually the area of triangle APQ. The area of triangle ABC is 24 square units. And it is equals to the area of the first shape, that is the area of triangle APB. This is triangle APB. The area of triangle APB equals to the area of triangle APB equals to the base AB times the height to the base SP over 2. AB is 6, SP is X, so into the divided by 2. So into the area of triangle APB equals to 6X over 2. This is the area of the first shape. The triangle ABC consists of. Plus the area of the second shape. Second shape is this triangle AQC. The area of triangle AQC must be equal, it is equal to the base AC times the height YQ over 2. AC is 8, YQ is X, and to the triangle AQC equals to 8X over 2. Plus the area of the fourth shape the triangle ABC consists of is actually the area of this triangle PBL. The area of this triangle PBL equals to the base BL times the height LP over 2. So it is BL times PL is X over 2. So it is BL times X over 2. Plus the area of the fourth shape that triangle ABC consists of is actually the area of this right triangle QKC. The area of triangle QKC in total equals to the base QC times the height KQ over 2. So it is KC times KQ, that is X over 2. So it is KC times X over 2. So the fourth shape that triangle ABC consists of, it is equals to KC times X over 2. Plus the area of the fifth shape, that is the triangle PQKL. We know that the area of rectangle equals to the length of the rectangle times the width. The length PQ is 2x, the width PL is x. And the area of rectangle PQKL equals to 2x times x. as they are the six-shaped triangle is equal to, so they are this triangle APQ. We already found out that the triangle APQ equals to 4.8x minus x squared. So in the next step, we'll simplify this side of this equation. So we have 24 equals to 6x over 2 is 3x, plus 8x over 2 is 4x, plus BL times x over 2 plus KC times x over 2. We take x over 2, the second factor from those two expressions. So what is left from this expression after we took from it x over 2 is second factor, what is left is actually BL, plus what is left from this expression after we took from it x over 2 is second factor, what is left is actually KC, plus 2x times x is 2x squared, plus 4.8x minus x squared. We continue to simplify this expression, this side of the equation. So 24 equals to 3x plus 4x is 7x. Here plus x over 2 times BL plus KC. So we have here one equation with one variable that is x. So we have to express the sum of those two lines with BL plus KC in terms of x. Otherwise we will not be able to solve the equation. Okay, we are able to solve an equation, one equation in one variable. Therefore we have to turn to express those two, the sum of those two line segments in terms of x. So what is the value of BL plus KC? This is BL plus KC. What is the sum of those two line segments? What is the value of BL plus KC? From the drawing it is very easy to see that if you remove from side BC this line segment LK, what is left is BL plus KC. Again, if we remove from side BC line segment LK, we left only BL plus KC. So BL plus KC equals to BC that is 10 minus LK that is 2x. So in total BL plus KC equals to 10 minus 2x. So we have x over 2 times BL plus KC, that is 10 minus 2x plus 2x squared plus 4.8x minus x squared. So we continue to simplify this side of the equation. So 24 equals to 7x plus, we have x over 2 times 10. We open the brackets here. 10 over 2 is 5, so in total this is an expression x over 2 times 10 is 5x. We have x over 2 times minus 2x. Minus 2 over 2 is minus x, so in total we have x minus x times minus x is minus x squared plus 2x squared plus 4.8x minus x squared. So 24 equals to 7x plus 5x is 12x. So we have here minus x squared is minus 2x squared, and minus 2x squared plus 2x squared is 0. So those three expressions will get cancelled. And we left only with 4.8x. Because 7 plus 5x is 12x. We left only with 4.8x. So in total we should find out that 24 equals to 12x plus 4.8x. So 20 So 24 equals to 12x plus 4.8x is 16.8x. So in total we actually found out that (24) equals to 16.8x. Here we divide this equation by 16.8 and get that x, that is the radius of the two circles, equals to 24 or 16.8 units in its length. Our task is to find out the area of this green shape. For the drawing, it is very easy to see that the area of this green shape in total equals to the area of the big right triangle ABC minus the sum of the areas of those two circles. Again, the area of this green shape equals to the area of the big right triangle ABC minus the sum of the areas of those two circles. So write it down. The area of the green shape in total is equal to the area of the big right triangle ABC minus the sum of the areas of those two circles. Because of the fact that those two circles are identical according to what is given as the equation, therefore the sum of the areas of those two circles must be equal to the area of one circle times 2. The area of one circle is of course pi x squared, and therefore the sum of the areas of those two circles must be equal to 2 pi x squared. This is also the sum of the areas of the two circles. This is 2 pi x squared. So the area of the green shape in total is equal to the area of the right triangle ABC, that is 24 square units in size, plus the sum of the areas of the two circles, that is equals to 2 pi times x squared. X is 24 over 16.8, and therefore x squared equals to 24 over 16.8 squared. So in total, the area of the green shape equals to 24 minus the value of this expression. This expression in total equals to minus 12.823 square units in size. Again, the value of this expression in total equals to 12.83 square units in size. (24) minus 12.823 in total is equal to 11.177 square units in size. So I can find out that the area that we are looking for in this question, that is the area of this green shape, is equal to 11.177 square meters in its size. So in the next step, as another lecture, we'll start with the first question, of course. Repeat on the solution of the first question. Our task in the first question is to find out the area of this semicircle. Yeah, our task is to find out the area of this semicircle that is inside the big quarter circle AOB. So this is a right angle because AOB is a quarter circle. OS equals to 3 units in its length. Is given us the question that RKQ equals to RQB. Now both the arcs of the big quarter circle AOB. Again, our task is to find out the area of this semicircle that is inside the big quarter circle AOB. So first of all, we define the center of this semicircle. This point is point C. We define the touching point of the quarter circle with this semicircle. This point is point P. Of course, the CP is the radius of the semicircle. It starts from the center and it's the point of the semicircle itself. So CP is the radius of the semicircle that we define as R. Likewise, CQ is also the radius of the semicircle that equals to R. So, in the next step, point S is the point of tendency obtained OB with this semicircle. In the next step, we join point C and S together by a straight line. Point C is the center of the semicircle, point S is the point of the semicircle itself, therefore CS is the radius of the semicircle that is equals to R. The radius CS that is equal to R, the radius CS is 1 to point S, that is the point of tendency obtained OB with this semicircle. And whenever your radius that is 1 to the point of tendency, then tangent to OB will be perpendicular to the radius SC. If OB is perpendicular to SC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did the construction, that is to say, from point Q, we go perpendicular on OB. Again, from point Q, we go perpendicular on OB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and OB. This point is point M. By doing this construction, we created quadrilateral CLMS. Inside quadrilateral CLMS, we have 1, 2, 3 right angles. 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, total must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. So 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral CLMS, we have 4 angles, and therefore we can relate to quadrilateral CLMS as a rectangle. So we know that quadrilateral CLMS is a rectangle, but before that, we actually join points O and Q together by a straight line. by joining points Q and O, we created the right triangle QOM. Point O is the center of the quarter circle, so angle AOQ is the center angle that subtend on RKQ. Okay? Angle AOQ is the center angle that subtend on RKQ. Likewise, we have center angle QOB that subtend on RQB. And because of the fact that AQ is equal to RQB in its length, according to Rule 23, here center angles that subtend on equal arcs are equal to each other. So in the moment we have a circle, this is the triangle AOB that subtend on arc AB. This is the triangle COD that subtend on arc CD. So if arc AB equals to arc CD in its length, then those two triangles must be equal to each other in their sizes. That is to say, alpha equals to beta. So we have those two triangles, they subtend on equal arcs. One equals arc AQ equals to arc QB. And therefore, they must be equal to each other according to Rule 23. So if we define this center angle as theta, then this center angle must be also equal to theta because they are equal to each other according to Rule 23. So theta plus theta equals to angle AOB, that is 90 degrees. Theta plus theta is 2 theta equals to 90 degrees, and therefore angle theta equals to 45 degrees. This is angle theta that equals to 45 degrees in its size. So in triangle QOM, the right triangle QOM, triangle 45 degrees equals to QM over MO. And right triangle QOM times 45 degrees equals to QM over MO. Times 45 degrees is 1, is equals to QM over MO. MO is 6, but I'll prove that MO is 6. So we substitute that M over 6, so 1 equals to QM over 6. We multiply this equation by 6 and I found out that QM equals to 6 units in its length. So Y97OM Y97OM equals to 6 units in its length in total. Because first of all, we know that OS equals to 4 units in its length. So if we implemented Taylor's theorem in our drawing, this we found out that SM also equals to 4 units in its length. Taylor's theorem is true for any three line segments that are parallel to each other. If we have three line segments that are parallel to each other, there are also other two line segments that connect those three line segments that are parallel to each other. We can implement rule Taylor's theorem. We know that, so I prove that PO is parallel to CS is parallel to SM. Okay, and so we know that PO is parallel to CS is parallel to QM. Line segment QP connects those three parallel lines together. Likewise, line segment MO also connects those three parallel lines together. According to this theorem, we have a special relationship between line segment QP and line segment MO that connects those three parallel lines together. The relationship is as follows: PC over CQ equals to OS over SM, and again PC over CQ equals to OS over SM. we need to test theorem. PC over CQ equals to OS over MS. PC is R, CQ is R, OS is 3. So if you follow that R over R equals to 3 over Sm. R over R is 1, so 1 equals to 3 over Sm. You multiply this equation by Sm, and finally found out that Sm equals to 3 units in its length. So prove that Sm equals to 3 units in its length, and therefore OM equals to 3 plus 3, that is 6. And we already proved that QM also equals to 6 units in its length, according to the equation that minus 45 degrees equals to QM over MO. Okay, so QM equals to 6, OM equals to 6. So here we already proved that polynomial CLMS is a rectangle because it has 4 right angles. But we know that the opposite sides of a rectangle are equal to each other. So in rectangle CLMQ, side CL must be equal to the opposite side SM, but SM is 3, therefore the opposite side CL must be also equal to 3 units in its length. Likewise, according to the sum rule, in the sum rectangle CSML, side CS must be equal to the opposite side LM, but CS is R, therefore the opposite side LM must be also equal to R units in its length. What is the length of this? Between 9 cement LQ, LQ equals to LM minus LM. Yeah, LQ equals to QM minus LM. Again, QL equals to QM minus LM. QL equals to QM minus LM. QL equals to QL equals to QM minus LM. So QL equals to QM, that is 6, minus LM, that is also. In total, QL equals to 6 minus 1 units in its length. In the next step, I copied the right triangle CQL, the right small triangle CQL in the equation, implemented the reverse theorem in this right triangle CQL. Okay, this is the right triangle CQL, this is the code from the original drawing. Only to the reverse theorem in this right triangle CQL, CQ squared, that is the square of the hypotenuse, equals to QL squared plus CL squared. CQ is R, therefore CQ squared is R squared. And it equals to QL squared. QL is 6 minus 1, therefore QL squared is 6 minus 1 squared, plus CL squared. CL is 3, therefore CL squared is 3 squared, that is 9. So in total, if you found out that R squared equals to 6 minus 1 squared plus 9. We have opened the brackets of this expression, and I found out that R squared equals to 6 minus R squared. 6 minus R squared equals to 6 squared, that is 36, plus R squared, minus 2 times 6 times R, that is minus 12R, plus 9. So we have R squared on both sides of this equation. R squared will get cancelled. After we cancel R squared on this side of the equation, we have to nothing, that is to say 0. So 0 equals to 36 plus 9 is 45 minus 12R. So now if you hold on the 0 equals to 45 minus 12R, here we let 12R to the equation, if I hold on the 12R equals to 45. Here we divided this equation by 3, if I hold on the 12R over 3 is 4, so 4 equals to 45 over 5 is 45 over 3 is 15. So in total 4R equals to 15. Here we divided the equation by 4, and we found out that the radius R of the semicircle equals to 15 over 4 units in its length. On this, we found out the area of this semicircle. Actually, we know that the opening semicircle equals to the area of the circle that is pi R squared over 2. Therefore, the area of our semicircle must be equal to pi over 2 times R squared. R is 15 over 4, therefore R squared is 15 over 4 squared. So it is pi over 2 times 15 over 4 squared. 15 over 4 squared equals to 15 squared, that is 125, over 4 squared, that is 16. So in total, the area of the semicircle equals to 225 pi over 16 times 2, that is 32. So the area of the semicircle equals to either 225 pi over 32 square units in size, or in terms of numbers, the area of the semicircle equals to 22.09 square units in its size. We finished with the solution of the repetition of the solution of the first question. In the next step, I'll get on the solution of the second question. In the second question, our task was to find out the area of this green shape. Again, our task was to find out the area of this green shape. So, in the moment, we have the right triangle ABC, AB equals to 6, AC equals to 8. The hypotenuse BC is the missing side. Inside this right triangle ABC, we have those two identical circles. Repeat again, our task is to find out the area of this green shape. So first of all, we created the whatever storm on the right triangle ABC in order to find out the length of the hypotenuse BC. According to the Pythagoras theorem, in the right triangle ABC, BC square equals to AB square plus AC square. Again, the right triangle ABC, according to the Pythagoras theorem, BC square, that is the square of the hypotenuse, equals to AB square plus AC square. BC is the missing side, so electricity, so it is BC square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus AC square. AC is 8, therefore AC square is 8 squared, that is 64. So in total, BC square equals to 36 plus 64, that is 100. So BC square equals to 100. Here we took out all of this version. So we found out that the missing hypotenuse BC is equals to the square root of 100, that is 10. So BC equals to 10 units in itself. In the next step, we found out of this right triangle ABC, according to the rule that the area of the triangle equals to the base AB times the height AC over 2. ABC equals to the base AB times the height AC over 2. AB is 6, AC is 8 over 2. 6 times 8 is 48 over 2 is 24. So the area of this right triangle ABC is equal to 24 square units inside. In the next step, we found out the area of this triangle ABC, right triangle ABC, in a different way. We choose the base of triangle ABC is BC, so the height to the base will be perpendicular from point A, that we define as edge over 2. So area of triangle ABC, in total, if we choose the base BC, in total will be equal to BC times the height edge over 2. Okay, BC equals to the base BC times the height edge over 2. The area of triangle BC is 24, so 24 equals to BC, that is 10 times edge over 2. 10 over 2 is 5, so in total 24 equals to 5, 8. Here we divided this equation by 5 and found out that the height edge to the base BC, the height edge to the base BC, equals to 4.8 units in itself. In the next step, we define the center of this circle, this point is point P. We define the center of this circle, this point is point Q. We define the point of tendency of tangent BC with this circle, this point is point L. We define the point of tendency of tangent BC with this circle, this point is point K. We define the point of tendency of tangent AB with this circle, this point is point G. We define the point of tendency of tangent AC with this circle, this point is point J. We define the radius of one circle as X. Therefore, the radius of the other circle are also equal to X, therefore they are identical. Therefore, they are also the same areas. In the next step, we join points P and N together by side line. P is of course the radius of the circle. This is equals to X. The radius PL is equals to X. The radius PL is going to point L, that is the point of tendency of tangent BC with this circle. And whenever your radius is going to the point of tendency, then tangent BC will be perpendicular to the radius LP. BC is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points Q and K together by straight line. QK is the radius of the circle, this is equal to X. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. In the next step, we define the touching point between those two circles. This point is point M, and from point M we go perpendicular on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point M and BC. This point is point T. When doing this construction, you can do it two small quadrantals, quadrantal PMTL and quadrantal MQKT. In quadrantal MQKT, we want two parameters, and for this surface area, as we have to measure it inside, and therefore quadrantal MQKT is rectangle because it has four rectangles. Likewise, in this quadrantal PMTL, we want two parameters. And therefore this surface area also equal to 90 degrees inside, and therefore it is 4 rectangles, and therefore it is a rectangle. So both those two quadrilaterals are rectangles. So what about the big quadrilateral PQKL? Inside the big quadrilateral PQKL, we want 2, 3, 4 rectangles, and therefore it is a rectangle. Quadrilateral PQKL is a rectangle. What about this is angle PMQ is equals to 180 degrees inside, and therefore you know that any angle that is equals to 180 degrees inside, it is defined as a straight line. So PMK is one straight line. In the next step, proved in another way that PMK must be a straight line according to rule 10. Those two circles have external between them at point M, and therefore we can implement rule 10. I think we can rule 10. According to rule 10, if two circles start each other externally, then the straight line will connect the circles together, passes for their touching point. In the drawing, those two circles that have an external between them at point P. Point O is the center of this circle, point M is the point O is the center of this circle, point M is the center of this circle. The straight line that connects the circles together is called the straight line OM. And according to this rule 10, the straight line OM must pass for point P, that is their touching point. Again, the straight line OM must pass for their touching point, that is point P. Or OPM is also a line. Again, OPM is also a line according to this rule 10. So we can implement rule 10 in our drawing. When put it in our drawing, here the center of this circle is at point P, the center of this circle is at point Q. The straight line that connects the circles together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass for point M, that is their touching point. Again, the straight line PQ must pass for their touching point, that is point M. Or PMQ is also a line. Again, PMQ is also a line. So we proved in two different ways that PMQ is a straight line. If PMQ is a straight line, there is the PQ total is equal to PM plus MQ. PM is X, MQ is X, therefore PQ total must be equal to 2X. PQ equals to 2X. We know that the opposite sides of rectangle are equal to each other, so rectangle PQKL, side PQ must be equal to the opposite side MK, but PQ is 2X, therefore the opposite side MK must be also equal to 2X units in its length. In the next step, I copied rectangle PQKL in a new drawing, and in a new drawing, we construct the height to the base BC, the height edge to the base BC. Note that the height edge to the base BC equals to 4.8 units in its length. Again, edge equals to 4.8 units in its length. So, okay, this is rectangle PQKL, this is according to the original drawing. Know that PQ equals to LK equals to 2X, and we did construct the height to the base BC from the vertex A. So AT is the height to the base, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. So when doing this construction, we get those two quadrants. This is quadrant PJTL. Inside quadrant PJTL, we have 1, 2, 3 rectangles. Therefore, this fourth piece angle is equal to 90 degrees inside. Likewise, inside this quadrant JQKL with 1, 2 triangles, and therefore this 4 triangles is equal to 90 degrees inside. So both those two quadrants have 4 triangles, and therefore they are both rectangles. So if you follow to this rectangle PJTL, first of all, we know that the opposite sides of a rectangle are parallel to each other. So in the big rectangle PQ, in the big rectangle PQKL, side PQ is parallel to the opposite side MK. Those two angles are located between the parallels QK and KL. Okay, those two angles are both located between the parallels QK and KL. According to the rule, the corresponding angles between parallels are equal to each other. Those two corresponding angles must be equal to each other on their sides. But this is the right angle, therefore this angle is also equal to 90 degrees in size according to the rule that I mentioned. Likewise, those two corresponding angles are located between the same parallels PQ and KL, and therefore they must be equal to each other in their sizes. But this is the right angle, therefore this angle must be equal to 90 degrees in size. So we already found out that PQ equals to 2x. Those two angles are both right angles. In the next step, we join points A and P together with straight line. We join points A and Q together with straight line. The opposite sides of a rectangle are equal to each other. So in the small rectangle PJTL, side PL must be equal to the opposite side JT. But PL is x, therefore the opposite side JT must be also equal to x units in itself. AJ equals to AT minus JT. Again, AJ equals to AJ equals to AT minus JT. So AJ equals to AT, that is edge is 4.8, minus JT, that is x. So total we should found out that AJ equals to 4.8 minus x units in itself. The next step we focus on this triangle APQ. From the area of this triangle APQ, the area of triangle APQ equals to the base PQ times the height JA over 2. And again, the area of this triangle APQ equals to the base PQ times the height AJ over 2. Now triangle APQ equals to the base PQ times the height AJ over 2. PQ is 2x, AJ is 4.816, PQ is 2x, AJ is 4.816, divided by 2. So in total, I should find out that the outer APQ equals to 2x times 4.816 over 2. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled. And after cancelled 2, we have 2x times 4.816. We open the brackets here and find out that x times 4.8 is 4.8x, x times minus x is minus x squared. So in total, we found out that what I get APQ equals to 4.8x minus x squared, so it's inside. This triangle APQ equals to 4.8x minus x squared, so it's inside. So we find the point of tendency of tangent AB with this this point is point S. We join points S and P together by straight line. SP is the underscore the second this equals to x. Those two angles are both right angles according to 1. Likewise, we join points Q and Y together by straight lines. So QY is the underscore the second equals to x, and according to 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We join points P and B together by straight line. We join points Q and C together by straight line. By doing all those constructions, we divided the big triangle ABC into 6 parts. This is the first part of triangle ABC. This is the free triangle APB. This is the second part of triangle ABC. This is the free triangle AQC. This is the second part of triangle ABC. This is the triangle PBL. This is the first part of triangle ABC. This is right triangle, and this right triangle again cube PC. This is the fifth part of triangle ABC. This is the fifth one other PQ LK. And this is the sixth part of triangle ABC. This is triangle APQ. It's very clear from the drawing that the area of triangle ABC must be equal to the sum of the areas of the three shapes that it consists of. So in total this is equal to the area of this first shape, this is the triangle APB. Again, in total, the area of triangle ABC must be equal to the sum of the areas of the six shapes that it consists of. That is to say, must be equal to the area of the first shape, that is the area of triangle APB, plus the area of the second shape, that is the area of triangle QC, plus the area of the third shape, that is the area of triangle PLB, plus the area of the fourth shape, that is the area of the rectangle QPC, plus the area of the fifth shape, that is the area of rectangle PQKL, plus the area of the sixth shape, that is the area of triangle APO. So what is the area of the first shape? The area of the triangle APB. The area of this triangle APB must be equal to the base AB times the height SP over 2 AB6 SP6, so in total the area of this first shape equals to 6x over 2. Equals to 6x over 2. And the area of this second shape that triangle AC consists of, the area of this triangle ACQ equals to the base AC times the height by Q over 2. AC is 8, YQ is x, and in total it equals to 8x over 2. So the second shape in total equals to 8x over 2, plus the area of the third shape that triangle ABC consists of, and actually the area of this right triangle PBL that equals to the base BL times the height LP that is x over 2. So in total it equals to BL times x over 2. The area of triangle PLB equals to BL times x over 2. And the area of the fourth shape that triangle ABC consists of, that actually the area of this triangle QKC it's equal to the base KC times the height AH that is x over 2. So total the area of this triangle OKC equals to KC times x over 2. KC times x over 2. And we have plus the area of the fifth shape, that is the area of this rectangle PQKL. The area of the rectangle equals to the base PQ times the width PL. The base PQ is 2x, the width PL is x. So in total, the area of this rectangle PQKL is equals to 2x times x. So the area of the rectangle PQKL equals to 2x plus x, plus the area of the sixth shape that triangle is consists of, and roughly the area of this triangle APQ. The rectangle the area of the APQ in total is equal to 4.x minus x squared units in size. So in the next step, we simplify this side of this long equation. First of all, the area of triangle ABC is 24. And we have 6x over 2 is 3x, 8x over 2 is 4x, and here we have BL plus KC over 2. Actually, we took x over 2 as a common factor from those two expressions, so what is left from this expression after we took from it x over 2 as a common factor? What's left? It's actually it's actually BL. But what's left from this expression after we took from it x over 2 as a common factor? What's left is actually KC. We have 2x times x is 2x squared plus 4.8x minus x squared. we continue to simplify this expression. We have 24 equals to 3x plus 4x is 7x. Here we have x over 2 plus bl plus kc. We have to express bl plus kc in terms of numbers. So this is the sum of the graph of bl plus kc. From the drawing, it's very easy to see that if you remove from side BC this line segment NK, what is left is BL plus KC. Again, if you remove from BC this line segment NK, what is left is actually BL plus KC. Therefore, BL plus KC in total must be equal to the value of BC, that is 10 minus 2x. So BL plus KC equals to 10 minus 2x. We have 2x squared plus 4.8x minus x squared. So 24 equals to 7x plus x over 2 times 10 is 5x. And x over 2 times minus 2x. Here minus 2 over 2 is minus 1, so we have to leave x times minus x, that is minus x squared, plus 2x squared plus 4.8x, plus x squared. So we continue to simplify this side of the equation. We got actually the 24 equals to 7x plus 5x is 12x. And we have here minus x squared is minus 2x squared, minus 2x squared plus 2x squared is 0. So those two expressions will get cancelled, and we have to leave with 4.8x. In total, we found out that 24 equals to 12x plus 4.8x. That is to say, $24 equals to 16.8x. Here we divide this equation by 16.8 and find out that x, that is the values of the second that we are looking for, it is equals to 24 over 16.8 units in its time. And first we find out the error of this ratio. The error of this ratio equals to the error of the big triangle MC minus the sum of the errors of those two circles. So the error of the big triangle equals to the error of triangle MC minus the sum of the errors of the two the sum of the errors of the two circles. Those two circles are identical, therefore they must have also the same errors. Therefore, the sum of the errors of those two circles must be equal to the error of one circle, that is pi x squared, times 2. Sum of the errors of the two circles equals to 2 pi x squared. Error of ABC is 24. And we have minus 2 pi times x squared. X is 24 over 16 on side, therefore x squared is 24 over 16.8 squared. So total we should also that the ratio equals to 24 minus this expression. This expression equals to 12.823. 24 minus 12.823 equals to 11.177 inside. So if you follow that they are this ratio, that is the error that we are looking for. This expression is equals to 11.177 units inside. Thank you very much.